Hi, everyone. I've had a few good questions about the equilibrium law and just exactly how things work with the constant and the ice table. So I thought I'd cover two of those questions in this video. The first has to do with the constant and the direction of the reaction. So here we have an equilibrium system. On the left-hand side, we have carbon dioxide. On the right-hand side, we have two substances, carbon monoxide and oxygen gas. And I've given you the K value for this equation. Now that K value, that equilibrium law constant, is referenced to how the equation is written as we see it here. So this constant would be equal to the concentration of carbon monoxide gas squared multiplied by the concentration of oxygen gas divided by the concentration of carbon dioxide gas squared. When you create your ice table and you're putting the positives and negatives in for the change, that does not affect this constant or the equation at all. Okay, don't start flipping things around because one side's increasing, one side's decreasing. That's why we use the term system rather than reactants and products, because all three of these chemicals are present at equilibrium, and both forward and reverse reactions are occurring at the same time. If we were to reverse how this reaction is written, then the K value would change as well. Let's just quickly take a look at that. Okay, I've written the equation again, but I've just reversed it here. From the perspective of equilibrium, there's no real difference. The same three chemicals, the same two chemicals on one side, and the same chemical on the other. Since equilibrium can be approached from either direction, and at equilibrium, all substances must be present, this is exactly the same system. However, because we've written it differently, the equilibrium law equation changes. Now, since my carbon dioxide was on the right-hand side, it becomes the numerator, and my carbon monoxide and oxygen become the denominator. So you can see that my second equilibrium constant, which I've written K2, is the inverse of the first, K1. Because I've inverted the equation, I also have to invert the constant. This is a good example because my first equilibrium law constant up top here was quite a small number. Remember what that tells us from the equilibrium law equation. That tells us that the concentration of carbon dioxide is much greater than the products of these concentrations here. So what we'd say with this equation here, that at equilibrium, at whatever temperature and pressure we're talking about here, equilibrium is more heavily weighted to the left-hand side. When we flip the reaction and we invert the equilibrium constant, now we have quite a large value, which tells us that proportionally, the numerator must be much larger than the denominator. And that tells us that the right-hand side of the equation must be more heavily favored. So at equilibrium, at this temperature and pressure, proportionally, there's more carbon dioxide than carbon monoxide and oxygen. Now, hopefully you can appreciate that I've just said the same thing both times here, that carbon dioxide is more heavily weighted at this temperature and pressure. So the important idea here is that the equilibrium law constant is in relation to the equation as written. If you reverse the equation, which I don't recommend you doing for any of these problems, but if you reverse the equation, you have to take the inverse of the equilibrium constant so it applies to your new equation.